All right. I will start. Here we go. Heavenly Father, we thank you for this day. I thank you for the students. Again, I just pray that you guide our steps, help us to learn more about your creation together, help the students, encourage them if they're struggling, and we just pray that you be glorified in what we do this day, Lord. In your name I pray. Amen. So, let me begin. Example 1. So today we're talking about graphing. And functions. So example 1, I'll say f of x equals to 3 plus 1 over x minus 2 quantity squared. All right. Let's graph this thing, all right? So you can graph this. Here's how we'll do it. We'll think, well, this is like the volcano graph, right? Yep. And then we shift right. Two units. That gives me y equals 1 over x minus 2 quantity squared. And then up 3, right? And so that should pretty well give me the graph. So I'll draw it down here. 3-step process, yeah. So I start with the volcano graph, which has got vertical asymptote of 0, horizontal asymptote of 0. Looks something like this. Then when I shift right, that moves the vertical asymptote over to here, over to 2, right? The horizontal asymptote stays put. The graph then looks something like this, right? And then up 3, well then my vertical asymptote stays put at 2, but my horizontal asymptote moves up to here, yeah? And as such, I've got myself a somewhat okay graph of this function that looks something kind of sort of like this. So there you go. There's a graph of this function using transformations of graphs. This is what we did last class, right? So just another token example. I just wanted to have this as a point of reference. All right. Okay, so I want to talk to you a little bit about properties of functions. And so there are many properties you can describe of a function. But we can talk about an even function. We can talk about an odd function. We can talk about a discontinuous function. So let me describe each. All right, so an even function, how do we define this? An even function is one for which f of minus x is equal to f of x. An odd function is one for which f of minus x is equal to minus f of x. And both of these have to be true for all x in the domain. All right. This is even function. This is odd function. Sometimes I verbalize it as like an odd function. You can pull minuses out of the argument. Even functions eat minuses. Discontinuous function, how would I describe that? Well, to properly describe it, I need a discussion from calculus. But for our purposes here, we'll just say this. It has a jump in its graph. It has a jump in its graph. All right, so let's look at some examples of these, yeah? Example 1. Well, I already did example 1. Example 2. We could look at y equals to f of x, and this time we'll define f of x to be x squared. All right, so x squared, this is one of our standard examples. We know it. We love it. It's part of our, this is our happy place. So the graph of y equals x squared, it looks like that, right? So there's the graph. Is this an even function? Well, let's try it. Let's try it out. So f of minus x, what does that equal to? Minus x quantity squared, right? When you square the minus x, you get x squared, right? Because minus minus gives us a plus, so minus x squared is just x squared. But that is f of x, right? So therefore, f is even. All right. So f of x equals x squared is an example of an even function. Now, we can say more, right? Like if you look at this, if we take the point like here, a comma b, right? What other point is on there? You reflect across the y-axis over to here, you get the corresponding point minus a comma b, right? You can think about reflecting it. You can think about reflecting the graph over the y-axis, right? Basically trading a comma b for minus a comma b, right? If you do that, you get back to the same graph again, right? So if you reflect the graph over the y-axis, we get back to the same graph again. So this graph is said to be symmetric. It's symmetric with respect to the y-axis. So that's another way to describe an even function. It's a function whose graph is symmetric with respect to the y-axis, right? Any questions? All right. Example 3. I'll look at y equals f of x. This time f of x will be equal to x cubed minus x. X cubed minus x. Now, how do we graph that? All right, so the way we graph that is like so. This is y equals to x times x squared minus 1, which is x times x plus 1 times x minus 1. From that, I can see that there are zeros for this function of 0, minus 1, and 1 respective. Those are places where the graph crosses the x-axis. As such, they're of critical interest. Here they are, minus 1, 0, and 1. And so my graph, it looks something like this. All right? So there you go. Now a question. Do you guys like time travel? Some people do. Good, because that's from next Monday. Okay, so like I haven't explained this method yet, but this is how we're going to pair factoring with graphing, right? To graph a polynomial, you factor it. Factoring reveals where the zeros of the polynomial are, and that shows you where the graph has to cross the x-axis. You use that information together with like a sign chart where it's positive and negative to construct the graph. So it's very much related to the inequality, the sign chart inequality thing that you guys all got wrong. So there will be a chance to hopefully improve on those ideas because we need to in order to graph. But anyway, as I said, time travel, because I haven't really explained that yet. I'm just drawing the graph for you guys, okay? So if you don't follow what I just did in example 3 at the moment, that's fine. We're not there yet, okay? Except for me. I've been here for years. So, you know, if you did nothing but math your entire adult life, you'd get good at it too, right? So, now, is this even? Is this odd? Is it neither? All right, let's find out. So let's look at algebraically, f of minus x is what? We do minus x into the formula here, minus x cubed minus a minus x. What happens then? So I'm plugging in minus x into the formula for f, right? Minus x cubed is minus x cubed. English doesn't do it justice, does it? But that's plus x, like you said. Now, can we factor a minus out of that? We can. And what happens when we do that? We get minus parentheses x cubed minus x, yeah? Which is minus f of x. In other words, this function is odd. It's an odd function. It's an odd function because we just showed that f of minus x is equal to minus f of x. Right? If I ask you on a quiz or a test for an algebraic argument that a given function is even or odd, this is what I'm talking about. These are algebraic arguments that show the function's even. This is an algebraic argument that shows the function's odd, right? On the other hand, you could judge even or odd from the graph, right? A function is even if its graph is symmetric with respect to the y-axis. A function is odd if its graph is like this. What do you say? What is this? So if we look at the point a comma b, yeah? What's its partner with respect to this pattern? It's that there's also a corresponding point over here, minus a, minus b. So if you have this kind of pattern, if for every point, the negative of the point is also paired, right? Putting minuses on both the x and the y components of the point, then that kind of reflective symmetry is known as symmetry through the origin. So this is said to be symmetric with respect to the origin. A terminology which has always bothered me, but anyway, it's standard. Symmetric with respect to the origin is what people say. Right? I think that's kind of an odd terminology, but there it is. So symmetric with respect to the origin means you have an odd function. Es good? Es bueno. All right, now, example 1. You guys tell me, even or odd? Now that we've had this talk, you guys come back to example 1. Is it an even function? Is it an odd function? Even. So you're looking at this, but we should be looking at this. Is this a graph which is even? If we reflect this across the y-axis, we don't get back where we started. We get a totally new function, totally new graph. This is not symmetric with respect to the y-axis. If you take this point right here, right, the corresponding point over here, it's not on the graph. If it was symmetric with respect to the y-axis, there has to be a pairing of these sort of opposing points across the y-axis, right? And it's not symmetric with respect to the origin, right, either, because this point is not paired with a point down here. Right? And this point is not paired with a point down here. That would have to happen if it was symmetric with respect to the origin. But that didn't happen. It's not symmetric with respect to the origin. It's not symmetric with respect to the y-axis. This function is neither even nor odd. So there are functions which are neither even nor odd. This is one of them. Discontinuous is the next chapter in the story. I'm not there yet, but a lot of people would say that there's a discontinuity of this function at the asymptote. Yeah.
This is only because it's moved, right?
Oh, this is in fact even with respect. This is an even function. It's symmetric with respect to the y-axis. The reciprocal graph, since you asked me, is a good example. The reciprocal graph, right? This guy. This is an odd function. See, there's a pairing. This point pairs to that point. This point pairs to that point. Like it's symmetric with respect to the origin. The reciprocal graph is odd. The volcano graph is even. But shifted volcanoes or shifted reciprocal graphs don't have to be even or odd. Once you shift it, it spoils the symmetry with respect to the axis. Right.
That never applies to parabolas, right?
Say what?
To parabolas?
to parabolas. Are parabolas even? It depends on the parabola. Okay, so let's talk about discontinuous. Let me show you an example which is really different. This is called the ceiling function. So example 4. And so here's the notation. So it's like the ceiling, see this? So this is equal to the integer greater than or equal to x. It's the integer greater than or equal to x. So let me draw a number line to help us out. So -3, -2, -1, 0, 1, 2. Okay, great. Okay, so if I ask you what's the ceiling function of, say, 0.5, what would that be? What's the ceiling function of 0.2? What's the ceiling function of 1.7? What's the ceiling function of -2.2? What's the ceiling function of 3? If we can answer these questions, then we pretty well understand the ceiling function. So you guys tell me, what's the ceiling function of 0.5? Nope. It's the integer which is greater than x. So the answer for the ceiling function is an integer. What's an integer? I heard whole numbers, z, 0, plus or minus 1, plus or minus 2, these sorts of things, right? So counting numbers and their negatives, also 0, yeah? So the ceiling of 0.5 is what? No, it's either it's an integer, not a pair of integers. What's that? Plus or no, you got to pick one. You can't give me plus or minus 1. 1. 1. This is just a lazy way for me to write this. Like you could also write this as ... -3, -2, -1, 0, 1, 2, 3 ... This is, I just wrote plus or minus there as a convenience of expressing the set. So don't you guys are reading too much into that.
So say would be 0.2.
0.2 would also be 1, right? That's the next integer. 1.7 is 2.
Negative 2 would be, it's greater.
So where is negative 2.2? Negative 2.2 is like here, right?
Yeah.
So what's the next integer larger than that? It's negative 2, right? Yeah. And 3 is 3, right? So basically, this is the always round up function, unless you're exactly equal to the integer, in which case you keep it, all right? Anyway, okay, so now that we understand what this thing is, let's look at its graph. What's its graph look like, yeah? So let's look at y equals to the ceiling function of x. So looks something. Let's see, 0 maps to 0, right? But then anything larger than 0 maps to 1. 1 maps to 1. Anything larger than 1 maps to, up till 2 maps to 2. Yeah, exactly, it's a staircase. Yeah, so it's like -1, 1, 2, 3, and so forth, yeah. And so forth and so forth and so forth and so on forever and ever, yeah? Infinite staircase is the graph of the ceiling function. So if you're looking for an example of a function with discontinuities, this is your guy, right? It's got tons and tons of discontinuities. There's a discontinuity at every integer. See that? We jump from, wait a minute, what happened there? Oh man, what did I do? Sorry, let me fix this. I got off track, guys. There we go. My apologies. I was like, wait a minute, that looks wrong. Oh yeah, I'm a dummy. There we go, now I fixed it. There wasn't supposed to be a double step right into the origin, That was dumb. Sorry about that. Okay, so there is a discontinuity in this graph at every integer, right? There's a jump. See, I'm graphing, jump, graphing, jump. So this is discontinuity. Questions? Okay, so the other question I ask here, just for the sake of, trying to refine our intuition and get better at questions about domain, what's the domain of this function? Can you tell me? Yeah, the domain here of the ceiling function is all real numbers, yeah. What's the range? It is not all real numbers. It's individual points, right? Which numbers does it hit?
All the integers.
All the integers, right. Yeah, it hits 0, it hits plus or minus 1, it hits plus or minus 2. Hits all of those, right? So the range here is actually the integers. So here you definitely don't want to use interval notation if you can avoid it, right? Interval notation is not the way to go for the range. It's a real pain to use interval notation here. Let's not do it. Okay, so
And just do it equal to z.
yeah, equals to z is the way to go. Of course, yeah. So one more example here. You guys ever done Build-A-Bear? Build-A-Bear? Yeah, we're gonna do build a function now. Okay, are you guys ready? It's very exciting. So this function, this example will cost you three times as much as a typical example, since you're building it. So like you should just overcharge, right? So that's how build a function works. Let's see here. So you're given this. So y equals square root of x, right? And I'll call this function f, all right? So part A, extend f to even g. B, extend f to odd function, let's call it h, all right? So I'm going to do this problem two ways. First of all, I'm going to do it graphically, all right? I'm going to graphically construct the rest of the story for part A. I'm going to graphically construct the rest of the story for part B. Okay, so this is given. So I want to extend f to an even function, right? I need to make the total graph that I'm constructing symmetric with respect to the y-axis, right? So all you do, it's pretty simple. You just reflect like that, right? And so there you go. That's y equals g of x, which is symmetric with respect to the y-axis, and therefore that g is even. Now the question is, what's the formula for it, right? I've drawn the picture for you, right? Let me finish the other one first. So how about odd? If I want odd, we have to reflect through the origin, right? So that would look something like this. And this would be odd. So now my question is, okay, great. What's the formula? There's the graph. I gave you the graph. Fine, we can all do that. We can reflect pictures one way or the other. Yeah, not a big deal. But what's the formula? I'll do the easy part. It's a case-wise defined function, yeah? So it's square root of x for x greater than or equal to 0. It's the square root of x for x greater than or equal to 0. But what's the formula for the case x less than 0? Can you guys tell me? See, because that's really what I'm interested in. What's the formula for the rest of the function? So the first section today, somebody told me minus the square root of x for this case right here. What do you think about that? Don't write this down, but can I do this? Would this make sense? Think about it. That would not make sense, because if you're in the case that x is less than 0, you can't plug in a negative number into the square root, right? Think about, yeah?
Would it be an imaginary?
That would be imaginary if I did that, so that's definitely not it. What is this here, though? This is exactly the reflection of that across the y-axis, right? That is the square root of minus x. So we want square root of minus x. And that'll do it. That's how we extend. That's an even function, which agrees with the square root on the positive numbers and extends to make it even, right? How do you get this graph here? What? It's like you take the square root minus x graph, right? And you flip it over the x-axis to get to here, if you think about it, right? So we could put minus the square root of minus x down here. And that would be the formula in that case, which you could understand from the transformation of graphing idea, right? We flip it and then flip it again to get down there. I think this is like much more intellectually challenging than my previous examples, right? There was no creativity involved here in the previous examples, right? Here I'm actually asking you to create something, given something to start with, right?
What if you then wanted to flip it again?
If I what?
What if you wanted to flip it again?
Flip what again?
The red line.
You want to flip it over here?
Yeah.
Well, then you wouldn't even have a function. You'd have,
Yeah.
you know, you'd have, if you go from here over to there, right? If you start with y equals minus the square root of minus x, right? And you flip it over the x-axis, that gives you y equals to minus the square root of minus x, yeah? Which is this minus the square root of x, which is this graph. And in that case, if you want to talk about that, we can. I'll do it up here. This graph is x equals to y squared. It is the sideways parabola. And since you brought it up, this graph has actually symmetry with respect to not the y-axis, but the x-axis. See, symmetry with respect to the x-axis means that you can pair this point with that point, right? A comma b gets paired with a comma minus b. That's symmetry with respect to the x-axis. Why don't we talk about symmetry with respect to the x-axis for graphs of functions? Because they're not functions. If you can ask the question, if you have symmetry with respect to x-axis, that means that you have two pairs of points. You have 2 points with the same x value and different y values, which means it's not a function, right? So that's why we talk about symmetry with respect to the y-axis, but we don't talk about symmetry with respect to the x-axis unless some student asks some kind of question which makes me digress, which I love, right? So this has happened in section 1, this happened. I talked about this. Section 2, I did not. And now you guys, I talked about it. So there's like a 1 out of 3 chance I'm going to talk about symmetry with respect to the x-axis in this class, I guess. But this won't come up again because that's not a property of a function of x, yeah?
Okay.
So, yeah. Anyway, listen, you can take a given graph and you can keep transforming it to new graphs all day long, right? You can keep moving it around and flipping it over and shifting it. Like, you can stretch it out and you can do these things if you want. The question really, of course, is like, what was the question asked, right? So I wasn't solving a problem here. I was just responding to his question, right? And illustrating the ideas. You could call this, what's the format? It's not problem solving. It's explore and discover, you know? Okay. I'm going to erase. So I think... So that's more or less all I've got to say about graphing and properties of functions, right? But now I need to talk to you about function operations. Function operations and, well, a.k.a., well, and let's say new functions from old. Okay, so here's the context. Given functions f and g, we construct, or if you like, build, create, define, all right, new functions, f plus g, f minus g, a constant times a function, a product of f and g, and a quotient of f by g, and finally f composed with g. These are all new functions we can build. Let me just write down the names I just said. So this is the sum, difference, scalar multiple. So here I'm just multiplying by a number. Product, quotient, and this, I'll be a little bit more careful, composite of f with g, where g is the quote-unquote inside function. Here, on the other hand, f is the outside function. There is a difference between inside and outside, all right? How do you actually define these things, right? How do we define them? So here's their definitions. F plus g of x, what's it defined to be? F of x plus g of x, all right? Totally unsurprising. F minus g of x, f of x minus g of x, all right? Again, I don't think, if I didn't tell you this, you'd already know it, all right? Students don't really need to be taught this, I don't think. I think students know this already. Like, and what else would you mean by f minus g, you know? A constant times a function. What do you mean by that? Well, that's formula. This formula is just the constant times the formula for x. It's just, that's how that works. All right? I will allow it. F times g of x is by definition f of x times g of x. So this is the product. So the product of a function is defined by the product of the values of the functions being multiplied. Quotient, f over g of x is f of x over g of x. All right. So far, all of these, I think, are just kind of like, duh. All right. I mean, not surprising, really. In contrast here, if I look at f composed with g of x, this is equal to f of g of x. That's how that works. And g composed with f, in contrast, is g of f of x. And so that's saying something a little bit more complicated. It's saying you plug the formula for one function into the other. That's not as simple as just doing arithmetic on the formulas. You actually have to process something there. And now look at this, something else. F of x times g of x, right? These are just numbers. Numbers commute. So this is equal to g of x times f of x, yeah? And so since that's g of x times f of x, that's the same as gf of x by definition. In other words, the product of functions commutes. F times g is equal to g times f. The same is not true for composite, right? F composed with g does not have to be equal to g composed with f. In fact, seldom is it. So how about quotients? Is f over g the same as g over f? I mean, clearly not, right? If I have g over f of x, what's that? It's g of x over f of x, right? So I would say that the quotient of two functions is kind of more like a composite than a product, actually, in the sense that there's a difference between f over g versus g over f, right? But it's worse than that, right? Because of course f over g and g over f, you can relate the values pretty simply. They're just reciprocal, right? The relation of the f composed with g versus g composed with f can be really, really complicated. It's not at all obvious how they're related for an actual example. Let's see that, okay? So let's actually look at an example. So let's see here. What example am I on? 7? Sounds right. Let's look at f of x equal to the square root of x plus 3, and g of x equals to x squared plus 1. All right? So let's run down the list here. Let's calculate the formulas for all our new functions. Like, what's the formula for f plus g? What's the formula for f minus g? What's the formula for 3 times f? What's the formula for f times g of x? All right? What's the formula for f over g? You know, we can do all these. So you guys tell me, what's the formula for f plus g? It's just what? F of x plus g of x, which in this context is the square root of x plus 3, right? Plus x squared plus 1. There you go. And of course, the other one is kind of just the same thing with a minus, right? But be careful. That minus has to apply to both of those terms, right? So that's something to be careful of. Whenever you're subtracting a sum of things, make sure your minus applies to all of them, yeah? Because this would be, if you wanted to simplify this formula, square root of x plus 3 minus x squared minus 1, right? 3 times f, well, that's just 3 times the square root of x plus 3, and there you go, okay? fg, so there we just do the square root of x plus 3 times x squared plus 1. And let me just emphasize one more time that you can commute those by algebra, right? This is equal to x squared plus 1 times the square root of x plus 3, right? Which is equal to gf of x. So we can multiply one way or the other and we get the same answer, right? Multiplication commutes. F over g, what's that? I heard the square root of x plus 3 divided by x squared plus 1, right? And let's see here, while I'm at it, what would g over f be? The reciprocal of that, yeah. Now, something I haven't emphasized yet here, but perhaps I should, is that there are strings attached, right, to these formulas, especially the quotient one, right? Because in order for the quotient to be defined, what do we need about g of x in the first one? We need g of x to be non-zero, right? If you do division by 0, is not allowed, right? Still not allowed. Wasn't allowed on test 1, still not allowed now. So, but that's not an issue for this, right? X squared plus 1 is non-zero, so really no strings attached. On the other hand, this guy, -3, is out, right? Of course, before even that, what else do we need? We need x plus 3 to be non-negative anyway, in order for this to be a square root, which is a real valued thing, yeah? So the domain for this function would be like -3 to infinity. But anyway, I don't want to say too much about domain in this discussion. I'm really more focused on the formulas, all right? So how about composition? So f composed with g of x, how does that work? All right, so this would mean f of g of x, right? F of g of x. What is g of x here? It's x squared plus 1, yeah? And how does that work? F of x squared plus 1. That means we have to put x squared plus 1 in the place of x for the formula for f. So that would be the square root of x squared plus 1 plus 3, right? Which of course I could simplify. That's x squared plus 4, right? in contrast, g composed with f of x is equal to g of, what's f of x? Well, square root of x plus 3, yeah? So that, I have to put in the square root of x plus 3 in the place of the formula, in place of x in the formula for g, right? So I take the square root of x plus 3, parentheses, I square that thing, I add 1. Now it just so happens that that simplifies, right? The square root of x plus 3 squared is just x plus 3, isn't it? So this is x plus 3 plus 1. So as it happens, the formula for g composed with f here is x plus 4. Yep. Oh, that wasn't a question. That was stretching. Stretching is allowed, but it does come at the risk of confusing me. But by all means, stretch. It's part of good health. Not an endorsement of yoga. I don't endorse yoga. I'm not an Eastern mystic. I don't believe in that stuff. Just saying. Let's see here.
Not even for the health benefits?
Of course not. Why?
Just asking.
I mean, it's all like, baked into the Eastern mysticism,
You don't do it for the mysticism, just for the stretching.
How can you be sure? It depends on what you're doing, right? I mean, I'm all for stretching, just don't call it yoga. So, who am I kidding? I'm not for stretching, but anyway. So, what is not a stretch is the fact that the square root of x squared plus 4 is not equal to x plus 4, despite you guys doing this. So you're like, yes it is, because, well no, actually you guys won't even do that, but some of you think like this, yeah? And then you're like, x, and then 4. Okay, that you guys wouldn't even do that, right? You'd put a 2 here, right? But this is not allowed, it's not true. The square root is not, that's not a property of square root. The square root of a sum is not the sum of the square roots. You can't do that. If we could do that, then things would be ever so much more simple. But no, so these are not equal, right? F composed with G is not equal to G composed with F, is my point. All right? In contrast, multiplication commutes. So, you're like, why are you making such a big point about this? Well, I've taught this class before, and I know what's going to happen on the next test. Now, here's the question. Is me saying this going to cause it to happen or not? That's a question you can wrestle with, right? Because some of you, when I give you compose the formulas, what are you going to do? You're just going to multiply them, right? Others of you, this is a more rare error, I'm going to ask you to multiply them and you're going to compose them. That almost never happens. You always go with the easier thing, right? Because it's much easier to multiply formulas than it is to compose them, isn't it? So, I know, I understand my concern about yoga is not shared by a number of churches. There's plenty of churches with like yoga clubs and stuff, but I think it's just symptomatic of a greater lack of discernment in churches, honestly. I mean, there was a time that you would not have found a Dungeons and Dragons club at Liberty.
How do you
Nothing
feel
wrong
about
with it,
goat
though.
yoga? How do you feel about goat yoga?
Goat yoga?
Yeah.
Like the greatest of all time?
No, like actual goat.
Actual goats?
Yeah.
Is this like something you do to prepare them to be more succulent as you eat them?
It's just fun. Just do it.
Oh, you just do it? Like you get a bunch of pet goats and then you make them do yoga?
Basically.
Yeah.
Do you have to like
No, they don't do the yoga.
you do the yoga with the goats?
Yeah, with the goats.
With the goats.
It's more
That
like
is so weird.
You do yoga and the ghosts just vibe in the same.
Yeah, the goats.
Yeah, they lay or like climb on you.
Yeah, the ghosts do whatever the heck they want, and then
Fascinating.
you're trying your best.
You will change your mind on yoga.
Yeah.
Is there like also like cat yoga and dog yoga?
There are some weird.
Is there like yoga where like you do yoga in front of other people doing yoga?
I just up for yoga.
And then if you have like 3 yoga rooms, you could do like yoga on yoga on yoga. It's like a hall of mirrors, but with yoga. No? I don't know. I like the word yoga. It's a fun word to say. Okay, so guys, I did have another example to do today.
Do you think Dungeons and Dragons is bad?
Is Dungeons and Dragons bad? I don't know. Like, how much witchcraft is too much witchcraft? I don't know. Like, example 8. So, let's see here. So suppose you know f of 2 is 3, g of 2 is 7, and f of 7 is minus 8, all right? Suppose you're just given that, okay? Then we can do things like calculate what's f plus g of 2, what's f times g of 2, and I'm not sure, maybe we can calculate f of g of 2, maybe we can calculate g of f of 2. Which one can we, which one can't we? So how about the f plus g of 2? F plus g of 2 would be 3 plus 7. See, f of 2 plus g of 2, those were given, so that's 3 plus 7. The answer is 10. F times g of 2 would be f of 2 times g of 2, which in this case would be 3 times 7. And I heard a vote for 21. I'll allow it. F of g of 2 would be f, well, that's f of g of 2, yeah? This would be g of f of 2. So the above one is what? The below one is what? F of what? G of 2 was 7, so f of 7. And this would be g of 3. One of those we can calculate at the moment. One of them we can't, right? Which one can we calculate? The first one. Oh, f of 7 is, yeah, thank you. F of 7 is equal to minus 8. Well, how do I know that? Because it was given. All right. So what's g of 3? The answer is, who knows? Because we're not given a formula, right? Now, if I gave you a graph, right? If I told you the graph of g looks like the following. Let's see, g of 2 is 7. And maybe the function looks like this. I don't know. So here's y equals g of x. Then could you answer, if this was also given, could you answer the question, what's g of 3? G of 3 is, in this, if this graph is given, g of 3 apparently is 0. One more thing before we go today. I want to give you a useful trick, technique, if you will. This one, another way we could have done this one would be this, guys. F composed with g of x is really f of g, where g of x, where g equals to g of x, okay? Or you could say where g equals x squared plus 1 if you like. What is f of g? F of g, we understand. That means just take x and make it, did you pan over here? Thank you. Did you, so we just make g go in the place of x. So square root of g plus 3. That's easy, yeah? And so that is square root of x squared plus 1 plus 3. In contrast, g of f of x, we can think about that as g of f, right? Where f is equal to, what was it? A square root of x plus 3. And so what is g of f? Well, it is g squared plus 1, yeah? And that is the square root of x plus 3 squared plus 1, which of course gets us back to x plus 4. My point to you in this final comment for today is, if you're having trouble with composition of functions, a nice trick is just to make this substitution idea. Just, you know, like, don't think of it as the full formula. Think of it as just the letter G or the letter F and just shove it into the other formula. And then, of course, at the end of it, you have to undo it, right? You have to put in what the formula is. But this gives you a way to break the composition into 2 steps if you're having trouble with it. Now, if you understood what I did over here, great, more power to you. But this is a nice sort of algebraic path, yeah? So sorry for wasting time on my, you guys fished me into the yoga conversation. Oh, you can stop recording now.